No class on Monday, right?
Huh?
No class on Monday?
No, will be a class Monday, and it will be exactly this way. You have the option of coming here, you have the option of getting on Zoom.
Okay,
I'm on Zoom every day anyway.
I'll just come here for class. Cause why not?
Okay. So, I think you'll find this homework a little bit shorter, probably.
Yeah. homework was with,
Number one,
yeah,
5 with proof. Find all the ideals you see. We're fixing to talk about what ideals mean. It's kind of a special kind of subring. Let R be a ring. We define the opposite ring, R op, to be the same ring in the sense that the abelian group's the same. The elements are the same. The addition is the same. But we've got this fancy new operation defined by x circle y is yx. So basically, the multiplication reverses the order. So x times y in the opposite ring is the same thing as what yx would have been in the original ring. We also define the center of the ring to be everything that commutes with everything in the ring. So in particular, if this is a ring with identity, 1 is always in the center of the ring. Show that R op is a ring and that R op, so the opposite of the opposite is isomorphic. Not quite a surprise there. Show R is isomorphic to S if and only if the opposite ring of R is isomorphic to the opposite ring of S. Show that I is a left ideal of R if and only if I is a right ideal of the opposite. And finally, show that if I is an ideal of R, then Ri, the opposite ring of R mod I, is isomorphic to R op mod I. And finally, this is something where we talk about what needs to be a product of an ideal. Let R be a ring, let I be a left ideal, let J be a right ideal. And we consider the set here, IJ is all sums that look like this, sums of alpha beta, where alpha lives in I and beta lives in J. Show that IJ is an ideal, right? It is both the right and the left ideal. And show that if I and J are ideals of R, then the product two ideals in this sense here, this set of things here, is contained in the intersection. Yeah. Okay, so I think that'll be a little bit shorter homework for you all. Preparation for test set, please. Yes.
So the S is just a nondescript label.
Yeah, S is some other. Yeah. I didn't say it, did I? But S is just another thing. That's right. Okay, other questions?
Oh, I knew.
Okay. So let's continue with our adventure. Chalk here. Okay, so the last thing we talked about was we talked about this notion of subring. And I believe the last thing I left you with was
about homomorphism rings.
Right, so we talked about what it means to be a ring homomorphism. And the last thing that I defined for you is what was the kernel of F. So if F of RP is a homomorphism of rings, then the kernel of F is a set of everything in R such that F of X is 0. Now, last time we talked about subrings, and that subring is sort of a baby ring inside of a parent ring. The analog with groups, subrings, subgroups, kind of the same sort of analog. We had special kinds of subgroups called normal subgroups that were important. In this case here, if you remember, one of the things when we looked at normal subgroups was normal subgroups were always the kernel of some homomorphism. And the kernel of some homomorphism was always a normal subgroup. And what we're going to do is we're going to kind of mimic this with respect to rings. But first, I'm going to start off with something a little bit more general. Definition. This takes into account that rings may not be commutative, so it's something in my own personal work, or, well, I guess professional too. I don't think this much about rings that aren't commutative. A left ideal, I and R is a subgroup so I is a subgroup, so this, of course, the setup is just like subgroup, right? It's a subgroup, such that Ri is contained in I. This is actually stronger than a subgroup, right? Because what does it mean to be a subring? A subring means it's also closed under multiplication, right? So that would mean, for this to be a subring, it would have to be X times Y is always in I, if X and Y are in I, right? This is even stronger. This is like a vacuum cleaner.
Yeah.
This sucks everything in R into I. So not only is any two elements by, not only is their product in I, but not only that, if you take anything in X and multiply it on the left by something in R, it sucks it right into I, right? So this is what we call a left ideal, left from the multiplication of R on the left side. So a right ideal is a subgroup that sucks from the other side. And what is an ideal? If I say ideal,
No, I see what you can do.
a R is a sometimes people get really fancy and verbose.
Well, they said R, so I.
Uh,
Yeah, that's the ring,
no,
right?
you're right. You say I is a two-sided ideal. Or just an ideal. So if I ever use the word ideal without a descriptor to it, I mean a two-sided
Yeah.
ideal.
We're all R1,
yeah.
R2,
I-
R
Both a left and right ideal.
2 is this, is a subgroup of I.
Okay, so let me ask you a question here.
Commutative?
Right. If the ring is commutative, then it doesn't matter. If it sucks from the left, it has to suck from the right, and vice versa, because the order of multiplication doesn't matter. So when you're, the only time that you need to worry about this distinction of left and right ideals is if you're entertaining the case of the ring is not commutative, like a matrix ring or something like that. Let me give you one last bit of terminology. We say well, first of all, let me ask you this. Any ring has automatically two-sided ideals. Do I know what they are?
Probably the identity and itself.
Find the identity.
Probably the 0.
The zero ideal is always two-sided.
Yeah.
Anything from zeros, the problem there. And of course, the whole ring is also an ideal.
Yeah.
We say that I is a proper ideal. You could also say proper left, proper right. If I was proper if it is not the entire ring. Proposition. and T be rings. And F will form a there. We've seen something very similar to my conclusion here when we talked about group theory. I am going to image of F. What are you supposed to true about the image of that? In our sense of the word, a subring.
Oh, it is a subring because it goes to T, you know? It is entirely contained within T.
Two. Kernel.
The kernel of F probably be an ideal.
Uh, well, here's the cool thing about my proof is doing rings allows me to be lazy. It's I like to be lazy. The first thing I know is this is a ring homomorphism. So first and foremost, it's a group of words. It's a homomorphism of groups. So I know this just from what I've done before. The image of F in T is a subset. And baby, we're halfway there in a subring, right? All we have to do is show that it's closed under multiplication, right? So let suppose X and Y live in the image of F. What does it mean to live in the image of F? By definition, there exists A and B and R such that X equals F of A and Y is F of B. Agree? So let's just look at X, Y. By definition, that's what that is. And what sort of mathematical prestidigitation can I pull now? What is true about F of A comes out of B?
It's F of, well, H of B.
Which means that X, Y is in image of F as well. Because it's the image of AB. So image of F in P is subgroup. Subgroup is closed under. Okay, so far. Two. Okay. Once again, I am going to appeal to my laziness. We know that the kernel of F is always a subgroup of domain of the morphism. And in fact, kernel of F we did earlier was like a normal subgroup. We don't even have to worry about normality here because groups are different, right? So, but anyway, this is all I need is a subgroup. Now I need to show that this subgroup in fact sucks. So let R and R and alpha in kernel of F. Notice that F, Of R alpha is f of R f of alpha, because this is a homomorphism. Right. Also, I'm being super careful. F of alpha R equals f of alpha f of R, which is 0 times f of R, which is so alpha R alpha are both in kernel F. So isn't that? Yes,
Say subgroup, you're just talking about like R. Like with R addition, not multiplication.
that is correct, yeah. Let me make a remark. Some authors, or in some contexts, if you have a homomorphism of rings, so if R E a ring 1, and an F from R to T is a homomorphism, then F1R on T is off to the same. But I will make clear to you whether I'm going to assume that or not. And there's actually some important reasons why this might be true, but oftentimes in some books you might see homomorphism, and if it's got the identity, it might assume that you take the identity of the ring, the identity of the target ring. Okay, any questions? Let me give you a lemma. This will come up later. And it's a silly observation. But it always amazes me in mathematics how sometimes little silly observations can lead somewhere big. And we'll go somewhere big with this later. Lemma. Let's suppose that R is a ring with identity. And I are a left ideal. So in particular, this applies to any ideal, left or right, actually. I is equal to R. Well, I is not a proper ideal. It's full ring if and only if anybody give me a condition. Can anybody identify a condition? That is correct.
Oh, no, I see.
One direction is totally easy, right? That's easy, right? If they're the same and R has an identity, no problem. The other direction is the one. So what this lemma says is an ideal is proper if and only if it doesn't contain the multiplicative identity, which is a useful way to think about it. suppose that one is contained, one is an element of I, and let R be just any garden variety element of R that you want. Because this shows that since I is an ideal, it sucks. It sucks this R into I, right? It goes, one is in there. And so that means every element of R has to be an I. The other containment is by definition. And so there you have it. We'll use this later. Okay. Any questions? Okay, so I know I've mentioned this, not too much of a spoiler then. Ideals, and when I say ideal, I mean ideal, both left and right ideal. So a two-sided ideal. This is the analog of this is the analog of the normal subgroup, right? And what was the big thing that we could do with normal subgroups? If you had a group G and you had a subgroup N that's normal, what could you build out of that? You could build a quotient group. That was the big thing, right? And the whole thing with the quotient group was the multiplication had to be well defined. This is what you can do for ideals as well, and it's very analogous. So, proposition. Let us suppose that R is a ring and I is an ideal. And I and R is ideal. You know, actually, I had a graduate student many years ago, did a PhD. Anyway, we did some ring theory physics, right? That's what I did. And at the time, they had to send the dissertations over to have them checked for making sure they're correct. Well, and they sent the people that did the looking over the dissertations were in the English department. And so we sent this dissertation over to my PhD student, and everywhere in the dissertation, it was like statements like this: I is an ideal, I is an blah, blah, blah. And it came back from the English department with corrections that look like this. So we had like 150 corrections. So a little mild. Anyway, so I'm going to state it correctly. I really is an ideal. Then R mod I is a. This is also a ring. Now, for me to make this into a ring, I got to tell you how to add and multiply stuff. And actually, for me to tell you to add this stuff, it's going to be redundant. Remember, this is an old friend, right? Just think of this as a quotient of two groups. R is a ring, so it's a group. I is a subgroup, right? It's an ideal, so it's a subgroup. And the group part is an abelian, so this makes sense because this is a normal subgroup. I can write these cosets this way. I need to come up with something new. And this is nothing new. This is the way we did this before. This is an old friend group. But of course, I have to find how to multiply things. Now remember, folks, we're in math class. What's the easiest way you can see this? R1, R2 plus R. I like the cut of your jib, right? That's as easy as it gets, right? And yes, this is exactly what we want to do. So you add the cosets just the same way that you did before. And multiply, this here. Any ideals two sided. If I don't apply adjective to it, I need two sided. Okay. Proof. I will sketch this anyway. Let me point out again, at least half my work is done for me, because R mod I is a group under addition. This is something we've already done. We've established this.
So that's number one.
Right, so number one, that operation is good to go. It's a group, everything. What do we have to do? Well, I have to show that this is a ring in the sense of I've got to show this multiplication. Well, what do I have to show about the multiplication? First thing I've got to do is show something important. Well, I mean, not necessarily, because I don't assume the original, I don't assume the original ring has, I didn't assume that. No, actually, that's not gonna be so bad, right? There's one big thing. What was the first hill we had to overcome? Back when we did groups, normal subgroups. And we defined we defined this operation here. The first thing I had to do was establish what? Does anybody remember? I have to establish this is well defined, right? Because there are many ways usually to write this coset, different representatives. And so you might worry, well, if I pick R1, you pick R1 prime. I pick R2, you pick R2 prime. We're picking the same coset. It better turn out that R1 plus R2 plus I is the same coset as R1 prime plus R2 prime plus I. The multiplication has to be well defined. So we've got this licked. So the first thing to do, big star, check definition of multiplication is well defined. And I promise you, that's what's going to use the ideal. And I did say ideal here. I did say left ideal. We're going to need two-sided, and we're going to see that. So, suppose that I say tomato, you say tomatoes. These are two different, it's the same way to write this, and same here. We need to show, so the goal, AB plus I equals XY. Does everybody get the importance of this step? Does everybody understand what it is we're trying to show? Yes.
Yeah.
Okay, so
Like, I get that we're trying to show that it's well defined, but I'm gonna be honest, I'm still not.
okay, I'm gonna lock you up in a brick room, and I'm gonna say, I want you to compute this coset times this coset. So what do? You sit down in the brick room and you do this. And you heard, well, Jim's rule says this, so you get this. Now, maybe I am down a well somewhere, and it's how it means. And I need the same computation you do. Only there perhaps are infinitely many things in this coset. So the chances of me picking the same representative you do, almost nothing, right? I might pick this. These two are equal. Nothing wrong with your choice, nothing wrong with my choice. They're just different.
When you're saying those two are equal, you're saying that the cosets, not the A and X are.
I'm not saying the A and the X are equal. I'm saying the cosets are the same. That's
Oh,
right.
that's why you're talking about representative. You're saying that the cosets are the same even though they have different
That's right.
representatives.
So for example, in Z mod 2Z, the easiest way to, so one of the cosets is all the evens and the other's all the odds, right? If I say pick me a representative for the odd, I mean, if God were to do this, God would pick this completely random and it would be just some random huge odd number probably, right? Whereas a human being in our limited factors, we might pick one or something like that. But it doesn't matter. The two different cosets, when you do the operation, it has to give you the same thing.
Because
So
otherwise
you
it's
would
not a
have
function at all.
You said, well, okay, I'll pick two, my representatives are A and B, and so that's what I get. I'm in a different room, I don't know what you've done, but I've got the same cosets, and I get different representatives.
Right.
Mine barfs this out.
If those aren't the same, then it's not a function.
That is right, if those aren't the same, we've got problems, it's not a function, right? And that's what we're trying to establish, everybody,
Okay, that
Okay.
makes sense. Thanks.
and thank you for having the guts to ask for that, when I know that some of you others probably appreciate, how many of you appreciate him asking that question? Come on, be honest. Come on, I do. All right, so let's show this, right? Okay, what are these cosets? What does it mean for these same representative? Or to represent the same cosets? This means. And by the same token. Everybody agree with that? I mean, we can't just pick anything, they have to be in the same coset, and to be in the same coset, we have to have that going on. So let me make the following. So we've got both of these things in I, right? Now, since I is a right ideal, so I'll put this for emphasis. I is in fact an ideal, so in particular it's right ideal. We have that AB minus XB is in I. Because what I've done is I've multiplied this thing on the right by B. Agree? I get AB minus XB is in I. No problem. Agree with that? By the same token, since I is a left ideal, then I can multiply stuff on the left, and I get XB minus XY is in I. XB minus XY. Yeah. Because I can multiply this thing on the left. And that gives me XB minus XY. That's also one, right? This is why I need a two-sided, because I need to suck in the B from the right and suck in the X from the left, right? So what does this mean? These two things. AB minus XB plus XB that's Y is an I. Because this thing is I, this thing is I, and it's subgroups, when you add stuff up, it's in there. Therefore, AB minus XY is an I. And that's all we need, really, because what that means is since AB minus XY is in I, then the cosets AB plus I and XY plus I are the same. So multiplication is well I. Everybody okay with that? That gets me the well-defined. Now, once I've got well-defined, this, the ring part, I've already got its group. The ring part, it's all totally downward. And I'll take you through this rather quickly. It's not too bad. Because if X, Y, and Z and R, then I need multiplication associative, right? But this is not an issue at all, because this is x plus I times yz plus I. So that's the rule here. Which equals x times yz plus I, doing this multiplication here. And the multiplication in the original ring R is associative. And because of the associativity of the original ring, I can do this. All right, put parentheses. And this is so it's associated. And it just the distribution property follows. I'll just do one of the distributive properties. The other one is the similar. By definition, this is x plus I times y plus z plus I. Right? And by definition, I make this new animal by doing this. And what do I know? I know I've got the distributivity property in the ring, so I can multiply this through. And this is xy plus I plus xz plus I. Almost there. And this is x plus I times y plus I plus x plus I times m plus I. And I've distributed everything, right? I really need to do distributivity from the other side, but I think you guys get the gist of it, right? Okay, any questions on that? Let me make a remark, which is, once I make this remark, you'll think, oh, that's kind of obvious, but it's worth recording anyway. What are and I and R number one, if R is commutative, so is R I. Right? Because the definition just comes from the multiplication in the original ring. If that commutes, this is one. And two, yeah, if R has an identity, then R mod I has identity. Anybody tell me what the identity, what is it got to be? Something plus I. And it's easy to see that this function says the identity. Uh-huh.
That's the identity with respect to multiplication.
Absolutely, right. Okay. Now guess what we have covered? Isomorphism theorems. But you know what's cool about the isomorphism theorems, and this is one of the good things about algebra, is the theme will be very similar to what you've seen before. It's very analogous. So if you've got a feel for the isomorphism theorem groups, you got one for you. And by the way, if you want to take some time to look back at your linear algebra notes, at least when you get out of therapy, then if you look back at some of the theorems that you had back then, you will see that a lot of these things mimic the isomorphism theorems we've been in here. Because again, there are isomorphism theorems for that. That probably when you took 3110, they didn't, oh, these were the isomorphism theorems, but that's essentially what's going on. So here, just like for groups, here's the biggie, the first isomorphism theorem. Let's let R and T be rings and add the homomorphism. Those are the homomorphism rings here. Then we already know the kernel of F is an ideal in R, the image of F is subgroup of T. Then so you induce a isomorphism from R mod the kernel of F mod that T. And I also threw this in for good measure. Given I and R an ideal, there exists a subjective ring homomorphism. I survive and R I given by I survive or I'm not sure why I threw that in the first isomorphism there, but it's worth recording anyway. Okay. Let's talk about why this is true. There's not much to prove here because we did most of the heavy lifting earlier with the group part. We were earlier in the semester when we were back in this. So we have shown the relation. This is actually a function on a sort of relation. F bar from R mod the kernel of F to the image of F given by F bar of R plus kernel of F equals F bar is in fact a well-defined function. Not only did we show that this earlier, this was a well-defined function, we showed it's in fact an isomorphism. Isomorphism of abelian groups. So let's think about how this helps us. What do we need to do to finish off the statement of first isomorphism? What do we know? The function is well defined. The function is a homomorphism of abelian groups. And not only that, it's an isomorphism. This function is one-to-one and onto. what's left to establish this? All we have to do is show this is a homomorphism of rings and we're done, because we already know it's bijective. We already know that it's got the group part covered. So it remains only to show that this, function is in fact a, multiplication. So F bar, X, Y. So all we need to do is show that the sucker's homomorphism of rings and we're good to go. So let's do this. So F bar of X plus I, Y plus I, is F bar of X, Y plus I. So I've simplified this because this is the way that we multiply. And what is F bar of X, Y? Well, it's just F of X. See, it's actually done most of the heavy lifting, because you gotta worry about this being well defined, you already did. Now, what do I know about F? Well, my hypothesis was F was a homomorphism of rings, right? So I don't know much, but I do know that I can do that, because F is a homomorphism. And by definition, it's F bar X plus I times F bar Y plus I. And so we're done. This is in fact a homomorphism of rings. Okay. That remark that I put down there about the subjective ring homomorphism, see if you can prove that yourself. Next time, I will give you a neat application, but let me ask you this. I will give you a teaser. I'm gonna give you two equations. Such a good job. Let me point out that this first equation right here has a very simple solution, right? If you're gonna be really lazy, but y plus 0 is plus 1. Can you find another solution? Can you find a solution for a non-zero value of 5? See if you can do it. How about this one? This one doesn't have any solution. Is that a good solution? Gosh, this would be hard, right? Start plugging in things. Is a square minus 10 times a square, can that ever be 2? Is it possible? Huh. And you know, it's obnoxious, isn't it? Because there's infinitely many things to check. You're never quite sure if you're done. Or okay, we'll use a little ring theory next time to get to the bottom of at least this one. Okay, any questions? All right, well, you all have a good weekend. No math club today. Enjoy Halloween, and we will see you on Monday.
You're gonna have a day on Halloween, everyone.